Good afternoon, students. Welcome to General Chemistry 1 Lecture 5. It is so exciting. It is so good. It's so great to have you in lecture this afternoon. As I said earlier, lecture this week will take place virtually. We'll have lectures pre-recorded, and I'll send them to you, and you can engage with questions or engage using questions via email or through office hours. So as we begin, I will reflect on some of the great words of one of the former First Ladies of the United States of America, a great orator, a great lawyer, a great former First Lady. She has done well, and I think it's appropriate to reflect on some of her words. These are the words of the former First Lady, Miss Michelle Obama. She said, and I quote, "My parents didn't have that much money, and they never went to college themselves, but they had an unwavering belief in the power of education. And they always pushed me and my brother to do whatever it took to succeed in school." She further went on to say, "I knew my parents would not be able to pay for all of my tuition, so I made sure I applied for financial aid on time. And when I encountered doubters, when people told me that I wasn't going to cut it, I didn't let that stop me." So be encouraged today as we begin lecture. As I said earlier, my goal in this class is not to overwhelm you or to discourage you, but to help you become a responsible, ethical, and successful scientist. So, let's begin. As we begin, I want to remind everyone, you are not alone. This is an academic community. Remember to get help when needed. Reach out to the university services if needed. Never give up. Keep trying. We are here to help you be ethical, intelligent, and successful scientists. However, at the end of the day, you must be responsible, ethical, and hardworking. And the reason why I keep this picture of Werner Heisenberg on this slide is I am being very intentional. Werner Heisenberg, at the age of 25, became the chair in theoretical physics at the University of Leipzig. And at 32, he was one of the youngest scientists to receive the Nobel Prize. Keep this in mind. You can do anything if you put your mind to it. So keep trying, work hard, be disciplined, take notes, and study well in this class. And you will do well. So as we begin, I always like to show the structure because many of you expressed interest in healthcare careers. DNA is a very primary important basis, a very important, basically it provides or stores a lot of information in the cell. It is basically one of the units that is used for gene expression. It's very important, very, very important. And aberrations or mutations in the DNA have implications, whether they're downstream or immediate. Point mutations, whatever the case may be. However, I want you to look at this, and I want you to think about what atoms do you see, what functional groups do you see, and why do you think this structure is so important. I'll give you a few minutes and I'll let you think about it. Okay, very good. Hopefully you have seen that you have oxygen, phosphorus, carbon, nitrogen, hydrogen. Don't worry about the 5' and 3', that is for a different class. But you should see the functional groups of phosphates, amines. I'm not getting into the types of heterocycles there. But phosphates, amines, hydroxyls, those are the things I want you to see and look at. Okay. So this is just showing you a more detailed description of the DNA structure. About me, remember, I'm value driven. I want to have an impact in society using science principles. My values, my core values are respect, integrity, and excellence. So keep that in mind. Some roles I've served in I've been as an ACS Bridge Fellow, GEM Fellow, podcaster, and the list continues. Okay, the objectives of this class. The goal of this class is to teach the chemistry content in an engaging manner that is relevant to the Bahamian student and digestible for their understanding. The sequence is as follows. Understand the fundamental concept A. Practice problems relevant to that concept. Learn more nuanced details about each concept. And practice more complex problems that integrate the details and the fundamental understanding. So the practice problems, the first set of practice problems would be equivalent to the quiz I would give you. The second set would be equivalent to the homework set I would give you. And at each stage of this class, there's a degree of, it's somewhat iterative in that I look at the feedback, I look at what you're doing, and I try to assess how can I best help you understand the fundamental concepts and best help you understand the nuanced details about those concepts. So today, we will be discussing atomic spectroscopy and chemical bonding. Of course, we'll explore the fact that atoms give off characteristic colors of light, as seen with discrete when they give off light in discrete wavelengths, which occurs line spectra when appropriately stimulated using some type of high frequency radiation. Line spectra provide clues about how electrons are arranged in atoms. Experiments show that electrons exist only at certain energy levels around the nucleus, and that energy is involved in moving an electron from one level to another. The Bohr model of the atom pictures the atom as a miniature solar system with the nucleus of an atom as the sun, about which electrons like planets orbit. That's just relating it an analogy in a sense. In terms of what we're going to discuss today, I want you to understand how line spectra of elements relate to the idea of quantized energy states of electrons and atoms, and the Bohr model gives a good description, a good visualization of that. And I also want you to understand that's the main idea for today, and also how common kinds of radiation in the electromagnetic spectrum according to their wavelengths, you can order them according to their wavelengths or energy. So we're just going to quickly look back, and then we're going to launch forward. De Broglie's equation. Remember, we've talked about wave-particle duality, and de Broglie was one of the big players in developing those ideas. De Broglie's work is applicable to all matter. All matter of mass m with velocity v would give rise to characteristic wave-like properties. We already established, based off the particulate nature of matter, that they have particle-like properties, but we also are establishing or understanding that they have characteristic wave-like properties. Hence, we have the wave-particle duality, and those wave properties were demonstrated experimentally with the classic example of the electron with the 1927 Davis-Germer experiment. Okay, you can read more into that or listen to previous lectures to hear more about that. Okay, so atomic spectroscopy. Using quantum theory, we can explain the atomic spectra of atoms. Each wavelength in the emission spectra of an atom corresponds to an electron transition between quantum mechanical orbitals. If we substitute the expression for the energy for a specific quantized state into the expression for a change in energy, we get the following: E final minus E initial. Then you complete or you continue with working at deriving the expression. You get Rydberg's constant multiplied by the reciprocals of the final quantized state minus the reciprocal of the initial quantized state, and that gives you the change in energy associated with the transition. And this is an example of the equation, basically mapping or including Rydberg's constant and Bohr's descriptions. So that's a quick overview of what we will talk about today, but let's break it down. What is a spectrum? How do you create one? A spectrum is produced when radiation from such sources is separated into its different wavelength components. Line spectra versus atomic emission spectrum, or line spectra and atomic emission. A line spectrum is a spectrum containing radiation of only specific wavelengths. A continuous spectrum contains light of all wavelengths. So a line spectrum is a spectrum containing radiation of only specific wavelengths. And an example of that you see below with line spectra obtained from the electric discharge from sodium or hydrogen. Light of only a few specific wavelengths is produced, as shown by colored lines in the spectrum. A continuous spectrum contains light of all wavelengths. So, atomic spectroscopy is kind of like an umbrella idea. But when we really delve deep into it, and when we understand what is the model that I can use to really map these ideas onto, what is the fundamental concept that I can map these nuanced details or map these nuanced implications onto. The Bohr model is that fundamental idea that I want you to get. The Bohr model was based on three postulates. Only orbits of certain radii corresponding to certain definite energies are permitted for the electron in a hydrogen atom. So here we have, just think of the key word here, definite energies permitted for the electron in a hydrogen atom. Keep those things in mind. Only orbits of certain radii. And then we also go to proceed and he said that an electron in a permitted orbit has specific energy and is in an allowed, keep that word in mind, energy state. And an electron in an allowed energy state will not radiate energy and therefore will not spiral into the nucleus. That's kind of how he packages idea in a classical framework. Then 3, energy is emitted or absorbed by the electron only as the electron changes from one allowed energy state to another. This energy is emitted or absorbed as the photon E equals h nu, and that's Planck's equation. So the ideas of Planck and Einstein, it's almost as if we're running a relay. And we're running a relay on the track, and the first runner who starts up the race is Max Planck, and Max Planck hands the baton on to Albert Einstein, and Albert Einstein takes the baton and goes on and passes it on to Niels Bohr. So just think about that in their mind in terms of how their ideas follow on, good way to process the concepts. And many people came after Niels Bohr. You could say that Schrödinger took the baton, or you could say that Heisenberg took the baton. A more direct analogy would say Heisenberg complemented to finishing the race, and Schrödinger also held complements finishing the race as well. But this is a good point to practice questions on Rydberg's equation, in which we say that 1 over lambda is equal to the Rydberg constant in brackets over 1 over the final quantized state minus 1 over the initial quantized state. And those values for each state are squared. So keep this in mind. The Bohr model had limitations. It only explains the line spectrum of the hydrogen atom well, and it avoids the problem of a negatively charged electron falling into the nucleus. Now, one can ask, why at that time were models explaining only the hydrogen atom well? Whether it is their computational power, you can say that may be a possibility, because also, if you think about it, if you think back in history, Schrödinger's equation worked well or worked best at the time for describing the hydrogen atom. However, as we gained more computational power, we were able to describe multi-electron systems or atoms with more than one electron. The thing to keep in mind here is that the environment, the resources, and the people who've gone before you, the ideas of the people who've gone before you, they kind of do have an effect on the work that you're able to produce. Yes, you do work independently, but in scientific discovery and scientific advancement, whether you see it this way or not, the community does play a part. The ideas from the community do play a part, and how you work with that community does play a part in how you advance. So at this point, there are so many implications we can gain from just looking at science history and also understanding the advancement that these scientists made. But let's talk about chemical bonding. Chemical bonding. What is bonding? We're going to discuss what is bonding, why is it important, what are the types, and what types and elements tend to participate in the different types of bonding. Okay? Bonding is a theoretical construct that involves the attraction of the electrons of an atom to the nucleus of another atom. Now, the reason why we use the phrase theoretical construct, if you think about it, as we've discussed earlier with Heisenberg uncertainty, you can't really say electrons in a specific position the entire time for the existence of an element, or existence of a molecule, or existence of a compound. But it gives us an idea of understanding how things are attracted and how things react. So that's why we describe it as a theoretical construct. Bonding is important because it provides a foundation for chemical reactivity. Bonding occurs as a means for elements to share, attract, or distribute electrons in order to become stable. So that's why it's important. Stability, just keep that word in mind. The types of bonding we're going to discuss in this class will be covalent bonding. And covalent bonding can, in a way, exist on the spectrum whether you have non-polar covalent bonding or polar covalent bonding, and you can look at the Pauling scale with the electronegativities to really tease out what type of covalent bonding you have. But in this class, we're just going to talk about covalent bonding strictly. That's it. In terms of that category. But for other types, you have ionic bonding and dative bonding or dative bonding. Covalent bonding occurs when atoms share electrons as a means of bonding. This typically occurs between non-metals and non-metals. For example, carbon monoxide. Carbon and oxygen are non-metals. Ionic bonding. An example of this will occur with sodium chloride. Ionic bonding occurs between metals and non-metals, sodium and chlorine, for example. This is the bonding between ions, so cations and anions. Dative or coordinate covalent bonding. This bonding that occurs is as a result of one element donating. So it's almost as if the bonds are the attraction that occur, and they typically consist of two electrons. That's how we map them out. That's how we describe them when we know them. So for a coordinate covalent bond, you have the entire bonding pair coming from one atom. And this typically occurs between metals and ligands or elements and molecules. You can think about some type of complex molecule, some type of complex crystal, or something of that sort. Just keep that in mind for coordinate covalent compounds. So now we're going to do a quick recap. We've discussed the main ideas for today: atomic spectroscopy and chemical bonding. Now we're going to do a quick recap. How many of you remember Heisenberg's uncertainty principle? How many of you remember Pauli's exclusion principle? Who remembers Hund's rule? What about Aufbau's principle? It's come from the German word aufbauen. What about wave-particle duality? Okay, so let's quickly recap. Heisenberg's uncertainty principle basically tells us that the more we know about the momentum of the electron, the less we know about its position. In that instant, we can't know them with the same degree of accuracy. And then, Pauli's exclusion principle tells us that no two electrons can have the same four quantum numbers. Hund's rule tells us that when you're filling degenerate orbitals, electrons fill them singly first with parallel spins. Aufbau's principle tells us you build up when you're filling orbitals. Now we have particle duality. Basically, we talk about that with the Broglie's ideas that matter has wave-like and particle-like properties. The classic example of that is when we look at a particle or the electron. So let's go back over these things. Solutions to Schrodinger's equation. You have 4 different types of quantum numbers I want you to understand this semester. You have n, the principal quantum number; L, the angular quantum number; m sub L, the magnetic quantum number; and m sub S, the spin quantum number. So the principal quantum number gives you an idea of the size and energy of the orbital. Those are the big ideas. N, size and energy. The angular quantum number gives you an idea of the type of orbital, that gives you a 3D understanding of the distribution of the electron cloud. And the value of L, it gives you an idea of what you're referring to. So L equals 0 for designated as S, L equals 1 designated as P, L equals 2 designated as D, L equals 3 designated as F. And S, P, D, F, those letters are derived from the descriptions of sharp, principal, diffuse, and fundamental. Then you have M sub L, which gives you an idea of the orientation of that orbital. And then you have M sub S, which gives you an idea of the orientation of the electron. So it's almost as if we're coming close, we're narrowing in, we're digging deeper. We're trying to better understand the electrons. We started off with the orbital, we looked at the orbitals, the angular momentum of the orbital, then we look at the orientation of the orbital, and then we look at the orientation of the electron. So instead of looking at orbits, we look at orbitals. So just keep that in mind. It's almost as if Niels Bohr got the baton, he passed it on to Schrödinger. But he not only passed it on to Schrödinger, he passed it on to Schrödinger and Heisenberg. So just keep that in mind. Just an analogy in terms of how a good way to process the ideas. From Max Planck to Albert Einstein to Niels Bohr to Heisenberg, to be exact. But that's a good way to put it. So yes, n can have integer values. Has integer values 1, 2, 3, 4. L ranges from 0 to n minus 1. M sub L ranges from minus L to 0 to plus L. And M sub S is plus half and minus a half. So what is it? Keep this in mind. Where have we seen this? Why should we care? And what significance does this have? So the principal quantum number n. The principal quantum number is an integer value that describes the overall size and energy of an orbital. The energy associated with the orbital is negative because the electron's energy is lowered by Coulombic interactions with the nucleus. Orbitals that have higher energy integer values for the principal quantum number have energies that are less negative. Moreover, as the principal quantum number increases, energy changes between the subsequent energy levels typically is less. What practical significance does n have? Now I want you to think about it. What practical significance does n have in your understanding of chemical reactivity and also orbitals in general? Okay, let's move on. Angular momentum. The angular momentum quantum number is an integer that describes the shape of the orbital. So we understand n is size and energy, L is shape, m sub L is orientation, and m sub S is spin of that electron. So it's an integer. L describes the shape of the orbital values and ranges from 0 up to n minus 1. The angular momentum quantum number, as a movable quantum number, gives us an idea of the angular momentum of the electron in the orbital. So think about it. If something is spinning as a distribution, probability distribution, or whatever distribution you look at, for this time, if you look at a specific place, you look at the probability distribution. If you look at any place, you look at the radial distribution. However, angular quantum number, it gives us an understanding of the shape of the orbital. So L equals 0 is designated as F, L equals 1 is designated as P, L equals 2 is designated as D, L equals 3 is designated as F. The letter designations, as I said earlier, were originally abbreviations from the words sharp, principal, diffuse, and fundamental. What practical significance does L have? Let's talk about M sub L. M sub L, the magnetic quantum number, is an integer value that provides information on the orientation of the orbital. The possible values range from M sub L, the possible values of M sub L range from minus L to plus L. The magnetic quantum number, so for example, if L is 1, it ranges from minus 1 to positive 1. The magnetic quantum number provides an understanding of the orientation of the orbital within a sublevel. As I said earlier, it can range from minus L to plus L. So the spin quantum number. The spin quantum number describes the orientation of the spin of the electron. Electron spin is a fundamental property. The spin quantum number has two possible options, spin up or spin down. So let's go back over these things. Heisenberg uncertainty principle. You cannot know with the same degree of accuracy in the same instant the momentum and the position of the electron. You cannot know with the same degree of accuracy or the same extent the momentum or the position of the electron at the same time. Or another way to put that is the more you know about the momentum, the less you know about the position of the electron. The Pauli's exclusion principle. We just discussed those four quantum numbers: N, L, M sub L, and M sub S. And Pauli's exclusion principle basically says no two electrons can have the same four quantum numbers, N, L, M sub L, and M sub S. And no two electrons can have the same four quantum numbers. Hund's rule. When filling degenerate orbitals, and we'll discuss this more as we delve deeper into electron configuration, electrons fill them singly first. And the classic example that's visual is if you think about the electrons when you're filling a p orbital, you put them singly first, and you put them, or you note them as parallel spins. So that's a practical consequence of Hund's rule. And then Aufbau principle, which comes from the German Aufbauen, which gives us an idea of how we build up when we are dealing with general orbitals and when we're dealing with writing the electron configuration. And the wave-particle duality. Wave-particle duality, as I said earlier, matter has wave-like and particle-like properties. And the classic example of that is with the electron, and you see this was demonstrated experimentally in 1927 with the Davis-Germer experiment. So we have discussed these things, and in terms of wave model, you can look back at the previous lecture videos, and you will see how there are caveats with the wave model of light that necessitated all of these ideations and all these other ideas. So once again, it's so good to have you in class today. I'm so excited to have you, so excited to be your professor this semester. It's a treat, it's a privilege. However, I need you to make sure that you are a responsible, ethical, and hardworking scientist this semester. You must work hard in this class. You must do your homework. You must do well in order for you to succeed in this class. Good to see you. Hope you're doing fine. Hopefully, you will understand the content for